So far, we haven't considered a potential problem that we might find in our training set. And the problem is that what if some of the counts are zero? This is also known as the black swan paradox. And it means that the fact that we do not see a black swan, it means that it has zero probability of appearing, right? So doing the analogy in our training set, if we do not see one case, it is not correct to assume that it's going to have zero probability of happening. Recall that our training sets are samples of the real general database that we expect to have in the future. So what we do to solve that problem, this is called the Laplace smoothing, and we just solve this by adding imaginary cases. So for example, when we were doing the counting of the restaurants in Santiago and low price, we always need to add one imaginary count such that we protect ourselves for cases in where these counts are zero, okay? So, and to be fair with all the other possible values, we need to add one imaginary count per case. So here we have for the location, Santiago, Vitacura, and Macul. It means that we need to add one imaginary count per each of these cases. So this is why we have +1 here related to Santiago, but divided by +3 here. So we are not playing in favor of any of the values. But with this trick, we solve the problem of finding cases in where these counts are zero, and this will send the probability to zero, in which case we wouldn't be doing the correct thing. So far, we have assumed that all our variables are categorical. When a variable is categorical, the simplest way to estimate the probabilities is by counting. So in other words, we are assuming a categorical distribution. It means that when we calculate the probability of the class estimated with the naive Bayes approximation here, this distribution in particular is being assumed categorical. So if we say that the probability of a given variable, let's say xj, is equal to k, given the class equal to z, and we assume that this probability is theta sub j, what we are doing is that assuming that this is categorical, we are estimating this probability as the count of cases in where the variable xj is equal to k and the class is z divided by the cases in which the class is c. As an example, when we want to calculate the probability of parking is yes, given that the price is high, we are assuming that this probability is categorical, is going to be theta, and the theta is going to be calculated as the cases in where the parking is yes and the price is high, divided by the number of cases in where the price is high. But what if we have a training case with continuous variables? Well, the simplest and good option is to assume Gaussian distributions. For example, in our naive Bayes approximation of the probability of the class, this term is going to be modeled with a Gaussian distribution. Recall that the Gaussian distribution has this probability density function, and it is bell-shaped, where this term is the mean and this is the variance, right? Given that it is a valid probability density function, if you integrate it between -infinity and infinity, we get 1. And if we were to calculate the average or the expected value weighted by the normal density, we get the mean, right? And the variance is exactly sigma squared. These two are parameters of the distributions, and this is why we put them here, right? We need those parameters in order to completely know the distribution. So here we have an example. Let's say we have these two variables, temperature and humidity, with a class play that might take values yes or no. So this plot shows an histogram of the variable temperature, showing in colors the two different classes, green for yes and red for no. Same thing with humidity. We have one distribution for humidity given yes and another distribution for humidity given no. So recall that in naive Bayes, we model each variable separately given the class. So what we're gonna do is, like for the temperature, we're gonna use one Gaussian for the temperature given the class equal to yes, and another one for the temperature given the class equal to no, and so on. Same for humidity. So we're going to have 4 different Gaussians, one per variable per value of the class. Recall that naive Bayes is assumed independence between variables given the class. It means that the variables are actually not independent from the class. So this is why we have different distribution per different values of the class.